introduce Jonathan Smith from GFDL. He, let's see, bachelor's degree, North Carolina A&T, master's Penn State, PhD from Howard.
That's right.
And he also spent time working here at Essex with CSES, working on I think air quality types of things and the GLM. And now he's at GFDL and he's going to tell us about great stuff he's doing with lightning, Dave. We're going to turn it over.
Go ahead. Up here, you can use the arrow key there.
So thank you guys for bearing with me. So I've been at GFDL for about a year and a half, working on comparisons of GLM data on the GOES-16 and 17 to model simulations of lightning frequency. And so I work closely with in the atmospheric chemistry group with Larry Horowitz, Vaishali Naik, and John Dunn there. So I'll just briefly go through the different data sets that I've used and the regridding, and then we'll take a look at a couple of parameterizations for lightning. A very familiar one is cloud top height. The simulation that I used the cloud top height parameterization. And then I've started to look at this proxy for lightning where you multiply CAPE, convective available potential energy, times total precipitation rate. So WMO has deemed lightning an essential climate variable. And so since we have this novel geostationary space-based data set, we wanted to compare that to lightning frequency within climate model simulations. That hasn't been done, at least the geostationary data has not been done to our knowledge. And then from there, we want to see how well model and OBS correlate. And so our larger goal is to use this to establish a framework for comparing other space-based lightning data sets to observations or to model simulations, and then also other atmospheric chemistry data sets. And then we will use this information in model development for lightning NOx parameterizations and also tropospheric ozone and methane estimates. So we use the atmospheric model, is the AM4 model in-house to GFDL. One of my colleagues ran this particular 13-year simulation from 2008 to 2020. Inside this simulation, we use a double plume convective scheme, and convective cloud top height is used for the lightning frequency parameterization. It has a more coarse resolution of 1 degree latitude by 1.25 degrees longitude. So we use four, I should say, space-based lightning data sets. We use the GLMs on both the GOES-16 and 17 satellites. It has a 2-kilometer resolution. And we use, we bring in polar orbiting data from the LISs on both the previous TRMM satellite and also the ISS LIS. So for the GLM data, we use the level 2 data. The GLM data is subdivided into events, groups, and flashes. So we use the flashes. The flashes are one or more sequential groups separated by 330 milliseconds and 16.5 kilometers. And so those are represented by the green X's you can see here faintly in this diagram from the Weather Service training guide here. And so you can see these grids more broadly in the GOES-16 here in this easternmost outline, and GOES-17 in this westernmost outline. And this is from the Wardlowski and Verts paper from 2021. So we use the flash locations as opposed to a gridded product like flash extent density, because we actually did do an iteration of calculating the flash frequency where we used the flash extent density, but our flash frequency calculation ended up far exceeding the climate model flash frequencies. So the level 2 flashes using that gave us a more comparable flash frequency. And as you can see, if you grid these locations, the values are far fewer than using the flash extent density. So we used climate data diagnostics operator software for our conservative regridding. The reason we used conservative regridding was because we had a very high resolution data set that we needed to get to more coarse model resolution. So the conservative regridding is taking the full and partial grid cells of the original grid here in blue, and so that would represent the GLM grids that are within the destination grid, which in our case would be the model grid. So that's taking the spatial average of those fine grids and taking the spatial average down to the destination grid there. So that's conservative regridding. So that was a necessary step to do for this in order to do the comparison. So the LIS data, it's polar orbiting. So on the TRMM, it's from 38 south to 38 north, and on the ISS LIS, it's from 55 south to 55 north. And it's polar orbiting, so that means that your viewing times are going to be higher or larger in the polar areas compared to the mid-latitudes and the tropics. And just one other thing to note is that we have to, with the polar orbiting data, we have to normalize that data for the viewing time. So it's relative to, flash frequencies would be relative to the viewing times, the varying viewing times here with latitude. So cloud top height, that's basically taking some storm dimension. So in our case, convective cloud top height, and relating that to flash frequency or electrical power within a storm. So that's from Price and Ryan 92. And several studies that compare global climate model simulations of flash frequency. And some of these are coupled with chemistry to trim LIS data, found that globally you get pretty good correlations, and also over land and not so much over ocean, except in this study, the Gordillo study, they vary the exponent here. So instead of to the 5th power, it might be lower to account for the difference in convection over ocean compared to land. So we've used cloud top height. So this is the flash frequency, flashes per kilometer squared per second. And my color bar here is 10 to the minus 14 to 10 to the minus 3 flashes per kilometer squared per second. So the top left is the model for December, January, February from 2018 to 2020. Then to the right of that is the GOES-16 GLM. Below that is the ISS LIS. And trim LIS to the left here for the same season, but for 2008 to 2013. So what you may notice here is that over South America, as you would expect this time of year, all three of these products show enhanced lightning activity. However, you do notice that the more enhanced lightning activity in the observations is to the east of where the model is saying that there is enhanced activity. So there is a discrepancy there that needs to be addressed. And so we move to June, July, and August. And so the same products here, we notice that as you would expect in the Northern Hemisphere, you have, and in the tropics, you have, enhanced lightning activity, and the quantities of these are similar. However, the observations are telling us that, especially in the Northern Hemisphere, the quantity of lightning is much more than what's predicted by the model. And here in South America, there are a few differences in the distribution of lightning, especially here in Eastern Brazil. And that might relate to, first of all, the low resolution nature of the data for the TRMM LIS, but then also the viewing times or the sampling in issues that occur with ISS LIS in this particular region.
Yeah, the South Atlantic anomaly.
Yes. Yeah, I would. You were asking a question there.
Yeah, what role is the anomaly playing in that? What you're seeing?
Yeah, I think it's. I would say that that has everything to do with this. I guess lack of a lightning observation here. That South American lightning anomaly does play a significant role there. So another way to look at the biases are to maybe take the base 10 log of the biases. So I'm calling that here the order of magnitude difference. And what I've done here is take the mean of the GLM, TRMM LIS, and ISS LIS biases compared to the model. And so on the top left is the, I guess, for the entire 2018 to 2020 time period. And then I go through the seasons DJF to SON. So I guess what we notice here is that the order of magnitude, there's a theme that you can see over South America. You have higher biases or order of magnitude differences in northern South America and also over the Andes. And in general, you have lower biases over the Northern Hemisphere, but especially in the warm seasons for the Northern Hemisphere. And so the scale here is from plus or minus 0 to 12, and between 0 and 1, I've modulated it or subdivided it a little bit, 0.25, 0.5, and then 1. So how do these observations and the model correlate? They're moderate correlations. So for the TRMM over the ocean, we find correlation generally above 0.5, except there for March, April, May. And then ISS-LIS is generally, pretty poorly correlated with the cloud top height parameterization within our model. And the strongest correlation we saw was for JJA over land for GLM. So these are for all of the grids within the GLM domain. But we said, well, let's look at the grids per hemisphere. So we looked at the Northern Hemisphere here, and the TRMM-LIS does a little bit better overall the grids in the Northern Hemisphere. That's better than just looking at both hemispheres there. It still does okay over the ocean, except for the summertime. And then the GLM does moderately well overall the grids in the Northern Hemisphere, except for March, April, May. And then looking at the Southern Hemisphere, the best correlations were with September, the grids in the Southern Hemisphere for TRMM in the fall season, or the, I guess this would be spring in the Southern Hemisphere here. And then TRMM does okay over the ocean in March, April, May, and June, July, August. And then ISS-LIS and GLM don't do well in the Southern Hemisphere. So we can move on to GOES-17 GLM. And what we find is when we look at the original grids, so this is the high resolution GLM 2 kilometers for GOES-17 GLM, there's a lot less lightning, but there are distinct lightning belts in the Southern Pacific and then along the CZ. And then the regridded version is here. And we have the model, which also picks out or I guess parameterizes these sort of belts of lightning in the tropics and Southern Pacific. And in general, what we find is that our order of magnitude differences across the GOES-17 GLM domain are between 0 and 2, plus or minus 0 and 2. And so that was for December, January, February. And for June, July, August, still the persistent lightning in those same areas. The model does seem to do pretty good in picking out the places where, you know, there's minimal lightning due to the, you know, the high pressure regions and the subsidence during this time of year in those regions. And again, the order of magnitude differences are fairly low. But unfortunately, despite that, those minimal order of magnitude differences, the correlations between GLM and the cloud top height are fairly low or fairly poor. And I guess what we are finding here is that when we calculate the flash rate, and so I'm defining flash rate here in this bottom table as the total number of flashes in the domain divided by the number of seconds of that time period, is that the GOES-16 GLM, the flash rates there per season and annually are comparable to the cloud top height in the model. And you saw that to some degree in the calculations, but for GOES or the correlations, but for GOES-17, it's the model predicts 2.4 to 4.25 times as much lightning. So we analyzed the cloud top height parameterization. And so we wanted to see, there are lots of other proxies for lightning. And one of those is Cape times a total precipitation rate. And this proxy was developed by David Romps. So in this image, or in this plot, in the left column over CONUS is the Cape times convective precipitation from North American regional analysis, and then compared with NLDN strikes, and these units are in kilometers squared per day. So spatially, you can kind of see the visual similarities in like the observation and then this proxy, and the R squared in this study between these two products, between the OBS and the reanalysis, was 0.83. So in 2014, David Romps, in a science paper, he ran several global climate models where he modulated the temperature and made projections for changes in Cape total precipitation and cloud to ground lightning for this 2079 to 2088 period. And so with a mean of all of these models of a mean temperature change of 3.6, sorry. This gave a increase in lightning of almost 12% for that change in temperature. And here, when he compared NLDN lightning in red, and sorry, this is a little bit hard to see, with Cape from the spark reanalysis and total precipitation rate from NOAA River Forecast Centers, he found that they both track pretty well together. When the Cape times precipitation rate goes up, so does the NLDN lightning, at least for the year 2011. So I pulled in era 5 Cape here, and also total precipitation. So we have average Cape for December, January, February for that 2018 to 2020 period, over 1,000 over the Amazon, which you would expect that time of year. And you'd also expect, this enhanced precipitation there. You have precipitation rates, exceeding 10 millimeters per day there. And then your Cape, your, I guess, most enhanced Cape kind of moves to the Northern Hemisphere over the Gulf of Mexico and the Western Caribbean here. And then you have pretty high precipitation rates in the tropics, as you would expect. And, over the Eastern United States, the precipitation distribution from season to season is fairly uniform. So it actually looks almost like DJF for JJA there. So what I did was I multiplied the Cape times that mean total precipitation rate, and also a factor of 7.8 times 10 to the -6 to get these per kilometer squared per second units. And so that multiplication is here on the left. And then I have the GLM flash frequency on the right from GOES-16 GLM. And what you can see is that spatially, there actually is a good bit of agreement, and also even quantitatively for this time of year. Also a good bit of agreement spatially for JJA. However, quantitatively, this, multiplying these two factors doesn't give you quite the same quantity. Maybe it's 2 to 3 orders of magnitude less compared to the observations. So when we look at the correlations, these are actually look at the correlation between these observations and the reanalysis, era 5 reanalysis. We see some maybe more strongly correlated, see a more strongly correlated relationship between these two than we saw with the GLM and the cloud top height parameterization in our model. So this seems to be fairly promising for our research, and this is something we want to, I guess, dig more into as far as looking at Cape and convective or total precipitation within our model. So I basically say that here. So just to summarize, we used conservative regridding to go from the high resolution to the model resolution. We saw lower biases over the Northern Hemisphere and higher biases over Northern South America. We found the correlation strength to be seasonally dependent, particularly with TRMM-Liz in the Northern Hemisphere, and then GOES-16 in the Northern Hemisphere annually, and overall in the summer. We see that the cloud top height parameterization in our AM4 model over predicts lightning over that GOES-17 GLM region. And that's probably two reasons for that. One is that it's largely ocean, so you won't have as much convection and lightning over that region. So those are kind of things we can really look into. And we found some promising or encouraging correlation strength when comparing error 5 reanalysis to total, well, we're multiplying the CAPE and total precipitation in the error 5 analysis and comparing that to the GLM and the GOES-16. And so there's several things we want to do. We're, I guess, working with Monty Bateman at Marshall Space Flight Center to see if we can get the varying detection efficiencies over both the GOES-16 and GOES-17 domains. And so that might help us in getting a more accurate flash frequency. And then, of course, examine the CAPE and total precipitation in the model. And then looking at other proxies for lightning, like cloud water path, and also ice mass flux, and even digging more into the cloud top height, where we might vary the exponent there. And then a long-term goal is to take do the same analysis for the lightning imager on the MTG satellite. So I think that's all. So sorry for the technical difficulties, and thank you for listening.
Thanks, Jonathan. So if anyone has any questions, either in person or online, our online attendees can post something in the chat. Just make sure it's to everyone when you submit it, and our in-person attendees can raise their hand. Oh.
Yeah, Jonathan, that's a really nice talk. How have you looked at some of the model predictors you're using? Do you have any information on how like those compare to, say, other models? Just to get an idea what the uncertainty might be.
I've really been focused on just this AM4, but I think that would be something good, like maybe looking at the CMIP data, and also the other global climate models. I think that would be a good idea. Yeah.
Nice talk, Jonathan. Question about the CAPE times total precip parameterization. Romps derived that based on just cloud to ground lightning that from the National Lightning Detection Network.
Yes.
Do you expect that that's going to work well with the AM4 model in predicting total flashes? I guess there's, of course, there's the ratio of intra-cloud to cloud to ground varies, quite a bit, geographically, and just wonder what you expect to get when you try it to predict total lightning.
Yes. So I think there would probably need to be some initial work done to, well, you know, GLM doesn't really or doesn't, it gives you total lightning, but doesn't distinguish between the two. So that would probably be a preliminary step to figure out how to parse cloud and cloud to ground lightning maybe before developing this Cape Times total precipitation into the model. Thank you.
Great talk.
Just add on to that. So I know Sarah Fairman and Bitzer they have a paper on the ICCG classification for GLM. And also we're working on the classification of GLM as well. So you might want to, you know, run a machine learning model before you know, do the calculation. The other thing about the trim lists that are more consistent with the your model, I think because trim lists, what you're using is their gridded data instead of the L2 data, and they did smoothing method for the gridded product. So that might be why they're more consistent than the L2, like the ISS list and the GLM data. That's what I think. I don't know, but that's what I think.
Thank you.
I guess I had a couple of questions. The first thing I think you want to, I would want to know is the convective cloud top heights from the model. How well do they themselves compare to observations? So you can kind of determine what percentage of your error is due to your flash rate scheme versus just biases in your model convective heights. So I would probably look at that. Another thing I'd be interested in seeing is that's kind of some probability distribution functions of your flash rate to get an idea. Because one of the things we found years ago with the cloud top height scheme is your mean flash rates may look okay, but that's because there's a small amount of flashes a lot, you know, all the time, as opposed to seeing kind of these pulses that you might see associated with convective storms. So that's kind of another thing I would look at for diagnosing what's going on.
Yes, on the first point, read a paper recently by, I think, Zhang, where he used the GLM flash extent density and compared that to I guess cloud top height from the GOES ABI product. So I guess when you made that point, that reminded me of his study that would be good to kind of dig into and get those cloud top heights for the grids.
Yeah, I can compare those with the model. Yeah.
Thank you.
Any other questions? In person or online? Okay. Well, in that case, thanks everyone for attending our seminar. Thanks, Jonathan, for giving us a talk. We'll continue with our seminar series next week, and we have another in-person / hybrid seminar. That's the week after that, but you'll get emails about it. Thank you.